So if I find the second derivative and it's greater than 0, the graph is concave up. So concave up would look like that. Well, I kind of drew a parabola. It doesn't necessarily need arrows on it. If the second derivative is less than 0, so it's negative, the graph is concave down. Now I have a trick for that, because that's just memorization. My trick is I look at the inequality symbol. So for a greater than symbol, I look at it and I rotate it 90 degrees. So if I take that symbol and I rotate it like this, it's going to look like that, and it looks like concave up. So if I take the less than symbol and I rotate it 90 degrees, it's going to look like that. It looks like concave down. So that's just my trick. That's how I remember it without having to memorize this definition. A point of inflection is what we call a point on the graph where we change concavity. And we saw some of these when we looked at the graphs when we were doing the first derivative test on critical points. Some of them turned out not to be relative maxes or mins, and they were actually changes in concavity, because a critical point will give us a change in behavior. And that behavior change can be from increasing to decreasing, or it can be a change in concavity. So some of the trickier changes in concavity I have graphed here to show you when they might occur. So we've seen something similar to this one and this one, because those are where our first derivative, those are tangent lines I've drawn on there. And this one has a tangent line with a slope of 0, so it means the first derivative was equal to 0. This one the first derivative would be undefined, right? Something divided by 0, because it's a vertical tangent line. Now, if I look at this first graph I've drawn, that tangent line would not come from a critical point, correct? So using the first derivative to find the critical points would not tell me that this was a point of inflection. The second derivative is how we're going to get to find out where are all the possible points of inflection. But you can see all of these are points of inflection, because right there I changed from concave up to concave down. And right here I changed from concave down to concave up. And right here I changed from concave up to concave down. So they're all points of inflection. Okay. We're going to find the intervals of concavity and the points of inflection for the function x to the 4th minus 4x cubed. Now, the idea here is that you're doing this without looking at the graph. But I put the graph on here because I want you to see that it verifies what we're doing. You can always use your graphing calculator to verify the work that you are doing. So, if I'm going to find the intervals of concavity and the points of inflection, so in order to find the points of inflection, the changes in concavity, I can't find their intervals unless I know where they're changing, we need to find the second derivative. So I need the first derivative, which is 4x cubed minus 3 comes out front, I'm going to get 12x squared. And if I was asking you for relative maxes and mins, then we'd find critical points and we'd find them, but that's not what I asked for. I only asked about points of inflection and concavity, so we keep going to the second derivative. 3 comes out front. I get 12x squared minus 24x. And now I know that points of inflection occur where this equals 0 or is undefined. Well, I don't have a denominator, so I'm not worried about undefined. We're going to set it equal to 0. And I'm going to factor this thing so that I can find those possible points of inflection. I'm going to pull out a 12x, and that'll leave me with x minus 2. So my possible points of inflection, okay, not everything, just like not everything when we found critical points was necessarily an extrema, not everything that we get from the second derivative is necessarily going to be a point of inflection. They're possible, and then we have to test them and see if they are. They're going to be x equals 0 from that, and x equals 2 from my second factor. Now, just so I can illustrate something here, I'm going to go ahead and find my critical points from this one. If I factor this, I'll pull out a 4x squared. That leaves me with x minus 12. Nope, not x minus 12. I pulled out a 4. That leaves me with x minus 3. I'll have critical numbers at x equals 0 and 3. Okay, so this tells me that 0 and 3 could be extrema. They could also be nothing as far as extrema goes. I have 0 also as a possible point of inflection. So if it's not an extrema, probably going to be a point of inflection. 3 can only be an extrema. 2 could only be a point of inflection. 0, kind of got to see what happens with it. Okay, so what we're going to do is we're going to make our number line, and we're going to use the second derivative to test what's going on. So really what I'm interested in, if we're only asking for concavity, I'm only interested in 0 and 2. Actually, let me write those above the number line. Now, we got 0 and 2 from when the second derivative equals 0. So they aren't going to be the values I plug in to check for concavity. I need to test to the left and the right of them, just like we do for the first derivative test. But now we're checking the second derivative. So to the left of 0, let's go with -1. In between the two, let's go with 1. And to the left of the 2, let's go with 3. Now remember, 3 is possibly a relative max or min. But that doesn't mean I can't use it in the test for concavity using the second derivative, because a relative max or min will be either concave down or concave up. So it's okay for the second derivative. It just would not be okay for testing it for the first derivative. So when I do this, remember our second derivative is 12x times x minus 2. That's the factored form of it. And that's a little bit easier for me to see what the sign of it's going to be than if I plugged into 12x squared minus 24x, because then I have to do calculations with bigger numbers. if I plug a -1 in here, that part's going to be negative, right? If I plug a -1 in here, I'm going to get -3, so we've got a negative times a negative is positive. Now, instead of putting a plus symbol like I do with the first derivative test, because of the trick I use with the inequality symbol, I'm going to say that this is greater than 0. And if I rotate that thing 90 degrees, is this going to be concave up or concave down? Up. Okay, if I plug a 1 into my second derivative, this first factor is positive. My second factor is negative. So we are less than 0. Am I concave up or concave down? Concave down. So this is a point of inflection. I changed concavity from concave up to concave down. If we plug a 3 into the second derivative, 12 times 3, that's a positive quantity. 3 minus 2 is a positive quantity. So I'm going to get a positive. I'm greater than 0. So am I concave up or concave down? So we do that. Concave up. I have another point of inflection. So if I'm going to give the point, that means I need the x value, the y value. So we've got 0, comma something, and 2, comma something. And we get the y value that goes with it from plugging back into our original function, which was x to the 4th minus 4x cubed. If you plug a 0 in there, you're going to get 0. If you plug a 2 in here, 2 to the 4th is 16 minus 4 times 2 to the 4th is 8. 4 times 8 is 32. 16 minus 32 is negative 16. So those are my points of inflection.
What did you just plug in back into the regular equation?
2. So I asked for the points of inflection. There they are. But I also asked what are the intervals of concavity. So I am concave up, going from -infinity up to 0, and from 2 to infinity. I'm concave down, going from 0 to 2. Now, let's go back and look at that graph again. Okay, so on our graph, we just found that 0, 0 was a point of inflection. Well, that's occurring right there. And I see that as a point of inflection, right? I went from concave up to concave down. And I'm decreasing the entire time, so it's not a max or a min. Then, it's harder to see this one, but we said at 2, so right there, stop it, it's changing concavity again. Now at that point in the graph, my graph kind of looks like a straight line, but it really is, it's traveling down this part of the curve that is concave down, and it's switching to this part of the curve that's concave up. So that's my other point of inflection that we found. So the 0 that was possibly a max or a min turned out to be a point of inflection, and the 3 that was a possible max or min is right here and turned out to be a min, but we didn't test for that one because we were only testing for concavity and points of inflection. what's going on here. The second derivative test is like the first derivative test in that it helps us locate maxes and mins, relative extrema. And it makes sense. If the second derivative at a critical point C is greater than 0, that means we're concave up, then the function must have a minimum at that critical point. And if it's less than 0, which means we're concave down, then the function has a max at that critical point. But if the second derivative equals 0, the test fails, it doesn't tell us anything, and we have to go back and use the first derivative test to determine if that critical point is a max or a min. So you might just want to use the first derivative test every time. But just to show you how this works, we'll do one like it. And again, the idea is when you're working stuff like this, you're not supposed to really know what the graph looks like, but I want you to be able to verify that your work is matching up. So this is what this graph looks like. Negative 3x to the fifth plus 5x cubed. We're going to use the second derivative test to find the relative extrema. In order to do this, we have to find the critical points. So I get those from the first derivative. The first derivative, I'm going to have a 5 comes out front, so I'm going to get negative 15x to the fourth. Then a 3 comes out front, I'm going to get plus 15x squared. And since that's just a polynomial, I get the critical points from when it equals 0. And if I factor the right-hand side, I'm going to pull out a negative 15x squared. That's going to leave me with x squared minus 1 because I pulled out a negative and the second term was positive, so I have to make it minus 1. Well, now I see x squared minus 1 is a difference of squares. I can factor it further. That's x minus 1 times x plus 1. So my critical points, my critical numbers, are going to be x equals 0 from the first factor, x equals 1 from the second factor, and x equals negative 1 from the third factor. So, my critical numbers are my possible extrema. In order to use the second derivative test, we need to take a second derivative. My second derivative, so I'm taking the derivative of this right here. 4 comes out front. I'm going to get negative 60x cubed. Then a 2 comes out front. I'm going to get plus 30x. Now, we need to know the sign of this when we plug in the numbers, and it's just a little bit easier to figure that out if it's in factored form. So I'm going to rewrite this as 30x times 1 minus 2x squared. You don't have to do that because I didn't ask you for points of inflection. Points of inflection, I would have to do that and then solve, right? But we're not going any further than relative extrema, so I just need the second derivative to plug the critical points into it. So, what we're going to do is evaluate at those values. So, second derivative evaluated at 0, is going to be 0, because 30 times 0 is 0, and I don't care what comes after. 0 multiplied by anything is 0. What just happened? The test failed. Okay, so we're going to have to go back to the first derivative test to classify what's happening at 0, but we're going to evaluate the others. At 1, I get 30 times 1 minus 2. So 30 is positive, but times a negative number, we are less than 0. Sorry, let's write that as less than 0. So we get a max. And at -1, if I plug that in, 30x is going to be negative, and 1 minus, when I square the -1, it's going to be +1. So 1 minus 2 is negative. Negative times a negative is a positive. It's going to be greater than 0. That one gives me a min. But on this first one, the test failed. So we're going to have to go back to the first derivative test to figure out what's happening at 0. Now, when I pick my test values, if I just look at 0, I'm going to think, ooh, -1 and 1 are the best values to the left and the right of it. But those were the critical numbers, so I can't pick those. So let's go ahead and label the critical numbers, even though we already know what the other two are. I'm labeling them just so I don't use them. So what we want to use as test values is something in between those. So I'm going to pick -1/2 and 1/2. And the first derivative was -15x to the 4th plus 15x squared, which in factored form we saw was -15x squared times x plus 1 times x minus 1. Okay, so we're going to plug a -1/2 in here. When I do that for the first term, no matter what I plug in for this first factor, the value is going to get squared and be positive and then be multiplied by -15. So that factor is always going to be negative. Then I plug -1/2 into my second factor, and I'm going to get a positive number. And then I plug it into my third factor, and I'm going to get a negative number. So we have a negative times a positive times a negative. That is positive. I'm increasing. If I plug 1/2 in there, still going to have negative for the first factor. For the second one, we're going to have a positive. And for the third one, we're going to have a negative, right? Because 1/2 minus 1 is negative. So negative times a positive times a negative will be positive. So what's happening at 0? It's increasing the whole time. So is it a max or a min? It is nothing. Now it's actually a point of inflection, but as far as classifying extrema, it's nothing. So let's go back and look at this graph real quick and see that. So we saw at 1, we said we had a max. Well, that's right there. And at -1, we said we had a min, and I see it right there. And at 0, we said we have nothing. Well, I see that. That is not a relative max or min. What is it?
Point of inflection.
It's a point of inflection.